Hey everyone! So now that we've learned a little bit about orbit and played with orbits a little bit, learned some stuff about ellipses and the different parts of an ellipse, we're ready to talk about elliptical orbits, which describes far more of how objects are actually moving through space. And we'll also talk about Kepler's laws and how that allows us to predict how objects are moving out there. So let's start off. We've talked already about circular orbits, and circular orbits are nice and symmetrical and easy to analyze using centripetal force. Like, everything is nice and consistent there. But the thing is, in order to achieve circular orbit, a planet has to be moving through space at the exact correct speed, in the exact correct direction, which would be perpendicular to the direction of the radius towards the body that it's orbiting, and in the exact right location, the exact right distance away for that gravitational force for the star that it's orbiting to perfectly match the centripetal force needed to maintain that circular orbit. And so when that happens, like, that is glorious and beautiful and easy to analyze. But that requires some really specific, perfect conditions. And most of the time, we don't quite make it there to get a perfectly circular orbit. What happens more commonly, which you saw in the simulation, is that if things are just a little bit tweaked, we're not quite at the right radius, we're not quite moving in the correct direction or at the correct speed, is that what we'll end up with is an elliptical orbit. So this is much more common for orbiting bodies than circular orbits. Usually we have an elliptical orbit. Now, based on what you saw in the simulation, where would you expect the star or the sun or whatever's being orbited, the primary body, where in the ellipse does the primary body locate itself? So what we find is that, this is Kepler's first law. When planets engage in these elliptical orbits, the primary body that they are orbiting is located at a focus of the ellipse. So one of those defining interior points, one of those foci, that's where our primary body is. We do also have another focus there, which doesn't have anything. It's just there on the other side of the ellipse. Only one focus actually has a physical object there that is being orbited. So what that means then is that as the planet goes through this elliptical orbit, it gets closer to the primary body at some times and farther away at other times. And we call the closest point perihelion and the farthest point from the primary body aphelion. So Kepler's first law then is telling us that planets are actually moving a little closer and a little bit farther away from the objects that they're orbiting. Let's connect that back over to Newton's law of universal gravitation and predict, what does that mean about the gravitational force acting on a planet as it engages in this elliptical orbit? So we see that inverse square law coming into play again because the masses aren't significantly changing, but the distance between the primary body and the orbiting body is changing. And we see again that inverse square law. So what that means is that as planets get closer to their primary body, they're going to experience a greater gravitational force, which means they're going to experience a greater gravitational acceleration, and also means that they're going to be moving faster through space at perihelion compared to at aphelion. This brings us to Kepler's second law, which basically the main idea of it is that a planet will move faster when it's at perihelion, when it's closer to the object that it's orbiting, and it'll move slower as it gets farther away from the object that it's orbiting and towards aphelion. Now, more specifically, what Kepler discovered is that if we were to plot like where the planet is at one point, and then we waited some number of seconds and then plot where it is at this new time, the amount of area that's being swept out from that ellipse, that little segment here that we see, like in blue right here, is going to be equal to the area swept out during that same time interval anywhere else in its orbit. So if this blue area represents how far the planet traveled over the course of, say, 35 days, this green area also indicates how far the planet traveled over the course of another 35-day period. So, but basically that ultimately comes down to it's going to move faster when it's closer to the object that it's orbiting, when it's closer to the sun or the star, and then our planet's going to move slower when it's farther away. So that's the main idea. Lastly, we're going to talk about orbital period and Kepler's third law. Okay, and Kepler's third law, in its essence, just says the bigger the orbit, the longer the period, the longer it takes for the object to go all the way around and complete a full revolution. Now, to get more specific and mathy on it, what we find is that the semi-major axis cubed is proportional to the orbital period squared. Okay, or in other words, if I were making a graph looking at the semi-major axis of different orbits and the period of orbit for each of them, if I were to take that semi-major axis, or in other words, like the longest radius of the elliptical orbit, and cubed it, put it on the y-axis here, on the x-axis here, I put the period, I would end up with a quadratic relationship. But that's a lot of exponents and weird stuff. So the main thing that I want you to know is that bigger orbits take longer to make a full revolution around. That's the main thing. All right. So let's do a little bit of a check for understanding. So we've got 8 recognized planets in our solar system. The eccentricity of each of those elliptical orbits is shown in this table. First question is, which of these planets, based on this data, would you expect would experience the most significant temperature fluctuations as it goes through its orbit? Which one is the least stable and has a bigger difference between its warmest and its coldest days? So based on the data here, what I'm seeing is that mostly, all of these orbits are relatively low eccentricity. They're pretty close to circles, which is nice. So a lot of times we approximate them as such. But the one that's the least circular, the most eccentric, is Mercury. And what that means then is that Mercury has the most exaggerated ellipse and therefore has the most discrepancy in terms of how far it is from the sun throughout its orbit. And in fact, we'll see a little animation right here, which doesn't show the rate of travel at an accurate way. But what we can see here is that this definitely isn't exactly a circle. It's definitely elliptical, and we see that the sun is closer to the bottom of the ellipse. So when Mercury is down at the bottom, it's at perihelion, and it's going to be probably warmer because it's closer to the sun at that point. And then as it gets towards the top of that orbit, it's at aphelion, it's farther away from the sun. I would expect it to get cooler at that point. Now, for the record, Mercury just gets really freaking hot during the daytime, just regardless. But I would expect that based on the eccentricity of the orbit, it would experience a greater fluctuation than the other orbits, which are more circular and more consistent in their distance from the sun. Last question for you. Based on this information, do you think that Mercury spends more time at its highest possible daytime temperature, or does it spend more time at its lowest possible daytime temperature? Well, if we think about Kepler's second law, we know that Mercury is going to be moving faster through its orbit at perihelion when it's close to the sun, and slower at aphelion when it's farther away from the sun. So that leads me to expect that Mercury is probably going to spend more time at a lower temperature because it's moving more slowly when it's farther away from the sun. So it takes a longer time to come back around and get close to the sun. And then by the time it's at perihelion and it's close to the sun, it's zipping on through a little bit faster. So it's going to spend less time in such close proximity to the sun. All right, folks, that is it. Hope you learned something, and have a lovely day.